The objective for today is to do a full comprehensive review of vectors. We've been working on it for quite some time now. I think now we could just take notes on what we've learned. So first things first, what's a vector?
Aaron. Vector is a quantity that has size and direction.
Good.
Size, you put parentheses and magnitude. Do you want an example?
No, thank you.
Displacement plus velocity.
What do you mean?
Displacement and velocity. That's an example.
Oh, I see. Examples of vectors. Displacement is one, velocity is another. Good. Okay, how do we, let's backtrack. If I label this axis as x, what do the other x's have to be?
Y.
Okay, which one is y?
The vertical one is y. The horizontal one is z. No, I lied.
The up one.
Up one is z. The vertical one is z. The horizontal is y.
Why?
Because of this.
The little right hand.
Right hand. Right. You get it. X, this one has to be y, and this one has to be z, because it matches the right-hand rule. Okay. The unit vector in the direction of x is what?
1.
What do we call it?
I.
Initial displacement.
I. Good.
Oh, yeah, but it is what unit vector is. Tells the unit vector.
So true. But what do we call the special unit vector in the direction of x? What's the special unit vector in the direction of y?
J.
J. Good. And then z?
K.
Good. So a vector is described with components. We have the x component, the y component, and the z component. In column vector form, right, just the x component, y component, and z component. If I were to translate that into unit vector form, what would it be?
AI
plus A plus AJ plus J plus
You're almost right.
with the
Nope, the hats are already over our vectors.
What are you asking? That's all I remember.
So here we have ax, ay, and az, right? Because ax is the component of a in the x direction. So we have to say that a, the component of a in the x direction, attached with the x direction. That's what.
because it's attached to the I doesn't have to imply that it's in the next direction.
That's what I
Right, but if you were to say a,
there would be like 1, 2,
Because A.
like 3, like depending on the equation.
right. The idea is
Oh, I see
that
what you mean.
these numbers can all be different, and each one is associated with the component.
Yeah.
That's like if we were to just put a here.
Yeah, I got it.
Cool. When I write vectors out, what piece of notation do I need? Arrows above the vector.
Is the specific name for the arrows above them?
You just say arrows. Arrows, super important. If it's a unit vector, what do we use? The hats, specifically if it's a unit vector.
Will I be ask those questions like how to properly format these kind of things?
No, but it will be looking for notation. It will be looking for how you format.
Do they like dot points?
They will, yeah.
Or they, if you do it like not proper notation, will they cancel all points or they give you like half credit?
There depends on the problem. If it's a problem, like a short problem, they might dock you. They only award integer number of points. They'll never give you a half point. So something like that would do a lot of damage on like a 2-point or a 1-point problem, but not matter so much for the 7-point or 8-point problems. So it depends. Okay. We're talking about the length of a vector. How do we find the length of a vector?
The resultant vector,
Magnitude. So the length of a vector,
Oh, okay.
so the magnitude of A. What's the formula for that?
Square root of a squared. Or,
Cool. Good. How does vector AB relate to vector BA?
If negative BA would be the same thing as AB.
Right, negative BA would be the same as AB. Why does that work?
because there's
Same magnitude.
different
Wait,
directions.
wouldn't it not be negative
Exactly.
BA? It would be AB. What's called BA equals negative AB.
Same thing.
Yeah, you could, because if you were to multiply both sides of the equation by -1, it would still work out. But the point is, same magnitude, but exact opposite direction. Okay, good. If I said that vector A was parallel with vector B, how would you be able to show that? How would you show that? One is a scalar multiple of the other. And right, we've been using K for that.
Yeah. And then you just do AB, oh wait, A equals K.
If you can relate two vectors through a scalar multiple, then you can say that they're parallel.
So if K is the scalar quantity, like, can you go over like an example that way?
Sure. And we'll get to what you'd said in a second about the resultant vectors. We'll get to that. Exactly. If K is negative, they're going in opposite directions.
Resultant vector, just like we subtract it. Subtract it.
Okay. Before we talk about resultant vectors, what would we have to talk about before that?
Talk about
Position vectors. Good. What does a position vector mean? What do we use it for?
From the origin to a point.
Vector from the origin to some point.
Is there a name for like the end point?
Generally, we'll just call it P with coordinates x, y, and z.
So usually you go from like origin to P, so it'd be like
Yeah.
P arrow.
And the vector from O to P is just the vector with x, y, z as their components. Right, good. Cool.
The magnitude of the resultant vector. Oh wait, right?
So you
That's how you go by phone. So,
subtract
yeah.
the position vector of A from position vector of B.
So before we talk about the mathematics, what is a resultant vector?
It is.
Isn't that multiple position vectors together?
Right, it's
points.
exactly
It's
right.
between 2 points.
So it's not the distance, but it's the vector from one point other than the origin to some other point.
I have a definition written down here saying distance between 2 points is equal to the magnitude of the resultant vector between them.
That is true, but that is an extension of this. And what did we say vector AB is?
OB minus OA.
Good.
So why is it B minus A, not A minus B?
Good question. Well, whenever we're trying to find the length of something, let's say 0, 1, 2, 3, 4, 5, and I were to draw a line from 2 to 3,
Oh yeah, you'd say what's the distance you take?
the distance is 5, which is the whole distance, right? Because 5 is from 0 to the end, and 2 is from 0 to the beginning. You have to do end minus beginning.
Yeah.
So that extension is true just when we expand it to 3 dimensions. Good question. Okay. All right. Are we okay with what's up on the board now? I'm going to erase it.
Yeah.
Yeah.
Great. If you're watching this, you must be very bored.
Here we edit this part out.
No, I'm totally going to keep that part in
Why?
for funsies. Okay.
Oh my god.
Okay. Collinear points.
That's the thing.
That is the thing. What does collinear mean?
They share a point on line. They intersect the point on line. They
Okay.
intersect a line.
Right. Okay. Yeah. So if you have,
They intersect a line.
well, we would talk about the points and how many points will always create a line.
2.
2. If you have, well, 2, you can definitely create a line through those 2 points. But as soon as you add a third point, that's when you ask the question if they're all on the same line. So the idea is collinear points means that A, B, and C are all on the same line. So what's that process?
We first need to find out whether or not they're parallel.
Whether or not what are parallel?
We need to find the vectors, possibly, for example, AB, AC, BC, and find whether or not those are parallel.
Right, we need, how many, what's the minimum we need to find? 2. We only need 2.
Yeah, you're right.
Because it's all 3 of our points are contained. You could either do AB and AC, AB and BC, or AC and BC. The idea is that they share a common point. Right, so that's step 1. Step 2, are they parallel? So what equation would I need to form between AB and AC? You would not be wrong. what?
VA by this.
So that's to get the resultant vector, but
Same.
what?
Parallel to scalar multiple.
Oh, exactly. So if we're using AB and AC,
To each other
okay.
A
with,
variable.
with K or whatever. Wouldn't it sometimes be T as well if we're doing like a real life application for time?
No, no. I don't think it has the same implications that we use T for.
Okay.
Right, but you just need to solve for K that makes this true. If it's not true, then they're not collinear, right? So if there is a value for K that makes 2 true, what other reasoning point do we have to assert before we can make our final conclusion?
That it works and with the other vector DC.
Nope. So we showed that AB and AC are parallel. So how can we assert that A, B, C are all on the same line? Right.
Find out AC.
We need to assert that they share a common point. Because you can have two vectors that are parallel, but they're not on the same line. You need to show that they share a point and are parallel. Once you do that, then you can say A, B, and C are collinear.
How would we assume they share a common point?
Because that's how you solved for A, B, and AC. This is the vector from A to B, and this is the vector from A to C.
Can you do a practice problem next to this one step?
Yep.
Oh.
Okay, so we said collinear. And we also said, did we say parallel vectors for an example?
Yeah.
Okay, well that actually,
It applies to the exact same thing. So
cool, so we'll just do this one.
you just do the same thing.
You got it. Okay, and Armand, this is what you were saying. Distance between 2 points. So if we were trying to find the distance between 2 points, what would we do?
Magnitude of the resultant vector.
Right. If you have point A and point B, first find AB,
The magnitude of it.
then find,
Find AB,
Oh, the magnitude.
and then you would subtract position vector A from position vector B.
yep.
Okay.
Is that it?
That's it.
So that's what
Yeah, with the problems that you'll get, what they do are combine a lot of these sort of mini ideas. The challenge is to figure out which ones you need.
Yeah, they always do mix up.
That would be a bummer. I know, thank you.
You broke it.
Well, I broke it.
You say you broke it?
Oh, I'm an idiot.
Okay.
Who broke it?
You said you broke it.
Okay.
For you cheat?
Yeah.
Nice. Wow. You better cut that out.
Hmm?
You better cut that out.
What?
Apparently, according to Aaron, you were a really nice night.
Thanks. Okay.
Can you get mine out?
Cool. So the next thing we're going to talk is finding a unit vector.
Yeah.
Woohoo!
Oh, I have a way to create a unit vector.
And specifically, a unit vector
In what form?
in some
Oh,
direction
Is the form. Wow.
other than I, j, or k. So let's say in the direction of A, and it has components 3 to 6. Okay. Yep. How do we find a unit vector in the direction of this vector?
So you want to find, you want to create a unit vector with the, what's the length? Oh, so you find the magnitude first.
So right, first find the magnitude of A. So how do we do that?
So 3 squared plus 2 squared plus 6 squared is square root.
So square root of 9 plus
4,
plus
36.
good. And when we do that, we get the square root of
49, so 7, so it's 7.
wow, that worked out nicely, didn't it?
Where? Here.
Okay.
You have B, oh no, yeah, B.
So this is a unit vector, right? In the direction of A, right? So what are we going to use for the notation of this unit vector? Right, over what letter?
Oh, really?
A. Because it's in the direction of A, right? So we're going to say that this is the A unit vector. And what's
So 7 times.
It's equal to 7.
Flip it.
right?
B is equal to A times 7. What?
No. So we found that the length of this was 7, and we want to scale it so that the length of it is 1. So what do I have to do with the 7?
Divide by 7.
Divide by 7.
Oh, yeah.
So this is just 1 over the magnitude of A times A. So in this particular example, we have 3/7, 2/7, and 6/7. It's because it's the same as dividing by 7. Because the length of the vector before we do anything to it is 7. But we want to create a unit vector, so we want the length of it to be 1. So to do that, we divide all the components by 7. So we're scaling it down to 1.
And then if you put the 3, 7, 2, 7, 6, 7, and you find the magnitude of that, it should equal 1, right?
Yeah, because then you get 9 over 49
But, yeah,
plus
oh, yeah.
4 over 49 plus 36 over 49. And when you add it all up, it's the square root of 1.
That's what makes you did it correct. Check, right?
Exactly. Vector with a certain length in the direction of some other vector.
Oh, I have the definition written down for that.
So find B with magnitude
Okay.
K in the direction
Okay.
of A.
So vector B is equal to K times the unit vector A.
Exactly.
Yeah.
So-
sorry, I'm sorry.
No, go ahead.
When there's a hat over top of it, it's a unit vector.
Correct.
When there's a line, it's just a vector.
Right. The difference is that the hat specifically means that that vector has a length of 1. What's cool about this is if you create some other vector, which is a scalar multiple of that unit vector, that scalar multiple ends up being the magnitude. Because when this has a length of 1, so let's say k is 3, You're saying 3 times this thing, which has a length of 1. So B would then have a length of 3. Sure. No, that's fine. So step 1 here is,
You could also say like with magnitude 1 in the direction of A would just be B equals 1. Okay.
well, I'll do an example up on the board. So step 1 in this process is find that unit vector, which is just this other thing that we've done. That problem is an extension of this other one. 2, then multiply in K. So let's say find B with a length of 14 in the direction of A, which is the vector 3, 2, 6.
Say B is equal to
So,
14 times 3, 7, 2, 7, 6, 7.
right, we found the unit vector for A. We've already done that. And we're saying that we wanted to have a length of 14. So B would equal 14 times 3 sevenths, 2 sevenths, and 6 sevenths. Because we said this has a length of 1, and it's specifically in the direction of A. This scales it so that it has a length of 14. So how do we...
If it asks us now on a test, do we just say 14 times 1?
Well, no, because A1 is a scalar. The unit vector of A has a length of 1, but it has a specific direction to it.
Oh, okay. Oh,
So what do we do now?
multiply it out. B equals 14.
Okay, well, what's 14 times 3 sevenths?
21 7.
You could just simplify to 2 times 3 to 6.
Exactly. We have a shared multiple. So the 7s and the 14s cancel out to 2. We get 6, 4, 12. Because 14 times 3 sevenths is the same as 14 sevenths times 3, right? 14 sevenths is just 2. Okay, cool. How does B compare with the vector that we started with?
It's this scalar multiple by 2.
Right. Here the length is 14, whereas here the length was 7.
Wow.
Whoa. So we could have had a shortcut just by doubling the vector A, but that process works no matter what we choose the length of B to be,
Why are they for 7?
because that was our unit vector.
Oh, you used that one?
Yeah, so this is not A with a vector. This is specifically the unit vector of A.
Will there ever be a problem where like we don't have K, but we'll have like, I don't know, like, I guess not.
It's possible if I told you what B has to be. Okay. Are we okay with what's up on the board now?
Yeah.
Okay. Scalar product. This is the first time we multiply two vectors together. So if I have vector A, which is, we'll just do ABC for short, and vector B, which is D, E, F for short. What is A dot B?
Magnitudes times.
No.
Oh, no.
It's
So
the x of one times x the other
So
plus the
so
y of one.
AD plus B, E, I can't see the thing, but
This is initially,
plus CF.
figuring out like distance and speed.
What's that?
Scalars are like distance and speed, right?
Yes, yeah. So why is it called the scalar product? We're multiplying two vectors together, so why do we call it the scalar product? No, that's a good idea.
Tell us why.
What's the
I have no idea.
vectors on the left, scalars on the right. The result of this is just some quantity. More specifically, it's a scalar quantity. It's just a number. There's another way to multiply vectors together where we get a vector out of it. But here, we're just getting a regular number. But then, right, we can link the dot product to the angle between the two vectors. So like, let's say I had A, and that was B. And I wanted to find the angle between them. The product of the magnitudes times the cosine of the angle between them is equal to the dot product. So if we simplify all this out, the angle is the inverse cosine
8 times.
over
8 times. Oh, yeah, that. Be like, what is the absolute value?
right, the magnitudes. So out of this, we can get a very nice sort of property about the dot product. If A dot B equals 0, then A and B are what? Perpendicular, exactly. All right. Now, can we use this to show that two vectors are parallel? Yeah. It's more challenging, though, than the other way that we already know. Don't bother using this one. It's not that you can't. You fully are able to. It's just a lot more work. Okay. A couple other things. Vector line equations. What was that form that we used for vector line equations?
R equals A plus T.
That's what the book uses, and that's total. Well, sure, we'll write it. A plus KB is what the book uses. What's the one that we used in class?
Y equals MX plus T.
Nope. Right, because this is almost the same as our ordinary line equation. There are a lot of important differences. They're really not the same in terms of input-output, but the form is the same. And the idea behind M and B are sort of interchangeable. Bless you. Okay. When we start doing kinematics problems with these, that's just another word for physical problems involving moving things. So like when we talk about ships moving or helicopters or whatever.
Kinematics equations in physics. Anyone else here taking physics? No. First straight.
And it would probably be more appropriate to do R. So V, yes? Okay. V is the velocity, and R naught is initial displacement. And let me just write it down. Intersection of two lines parallel, and when with the intersection there's the special case of perpendicular. And if they don't intersect and they're not parallel, they are skew. Good. Okay, what we're going to do for homework is I'm going to type up a practice quiz that I will post to Moodle. It is your choice to do it and your choice to not do it. But I advise you to do it because on Wednesday I will give you a quiz on this stuff. Cool. Happy Monday, everybody.